Hello, test. Good afternoon, everyone. I think we should get started. Okay, good afternoon and welcome. This is Technical Session 1. I think we have people just coming in. All right. Okay, so we actually have three very interesting speakers, three very interesting talks on infrastructure security, CNF architecture, and Starlink performance from three very distinguished guests. So we have about 30 minutes, hopefully 20 to 25 minutes for each speaker, and then we will be allocating 1 to 2 questions after each speaker. So we should, I'm not sure if Jeff is in the room, we should probably get started. If he's not here, no? Okay. Get someone else. All right, so I think we will have Michael to start with. Michael Tadot, just introducing him for a bit. Michael is the Chief Technologist for Telco for the Asia Pacific region from Red Hat. Michael has vast experience in the telco industry and cloud-native technologies, and is part of the startup that pioneered Telco Cloud, which eventually became known as NFV. So here to talk about the evolution of virtual network functions to cloud-native network functions. Michael, you have the stage. Thank you.
Yeah, thank you. Okay. It's not showing here. What's going on here? Okay, go back. Sorry, some problems with the slides. Voila. Okay, thank you. So yeah, Michael Tadot, Chief Technologist Telco for Asia Pacific at Red Hat. It's an honor to talk at the EPNIC. It's my first time doing this. I understand here in the audience, we have mostly, I think, people dealing a lot with routers. In fact, I was myself working for a router company called Alcatel, then Alcatel-Lucent. So I know a little bit about the topic. And here I'm going to talk about, how this whole thing, networking has revolved from servers. Because I think at the very beginning, the internet was built using servers, and the routing was done, in fact, on servers. And then as I think the demand of capacity increased, in fact, people developed companies like Cisco developed appliances, the routers that probably most of you are using today. And we're kind of seeing, oh, this is going back to servers to some extent, to virtual machines, containers, and how this is going back. So I'll give you this, so that's the title of the presentation, from virtual network functions, VMs, to what is now, in fact, more, let's say, up-to-date and more relevant, cloud-native network functions. So that's it's kind of summarized here. In fact, before that, there were servers, in fact. Then we used to have, a lot of customized hardware. You have these ASICs made by companies such as Broadcom. Alcatel is still doing its own silicon for routing. And this network appliance area. And then around, let's say, year 2010, and the emergence of cloud computing, the success of AWS, people started thinking again, oh, should we not apply cloud computing, not just to IT, because cloud computing was first successful, I would say, in the data center with VMware, with server consolidation. Then AWS created public cloud computing. But why should we not apply the cloud computing principles to the network itself? Meaning that instead of using only appliances, why not put some of these functions, and at that time, around 2010, the prevalent, let's say, mode of virtualization was virtual machines. Why not put some of these functions, if possible, if they're mostly CPU intensive, on virtual machines? And now, after 2020, the next evolution of, let's say, hypervisor-based virtualization is now to use containers. And the fundamental reason is because Linux has won the data center operating system war. Everybody is using Linux. So in fact, you can share the same kernel. That's why, in fact, more and more containers are the method of choice for virtualizing software instead of doing VMs. VMs, you can have copies of different operating systems, but since everybody now is going to use Linux, why bother having several copies of Linux? You share the same Linux kernels, and the container is just kind of an isolated process. So now more and more workloads, in fact, are being deployed cloud native, and open source project that has won the container orchestration war is called Kubernetes. So everything is now being, new workloads are delivered as containers orchestrated by Kubernetes. Before, in the VM area, one of the very successful, of course there's VMware, but one of the very successful virtualization software was, and it still is, OpenStack. But now we are moving to a Kubernetes-based networking. And that's why, this area, we call it VNFs, Virtual Network Functions. And here we are going to cloud-native network functions. Some people call it container network functions. While in the first iterations, so you implemented virtualized network function as a set of VMs running on OpenStack, sometimes also VMware, dependent, but at least from the open source projects, mostly OpenStack. Then there were the first implementations of workloads who are containerized. And in fact, the container distribution itself was running on top of a virtualization of a hypervisor, in this case, OpenStack. And in fact, more and more the trend is to get rid entirely of the hypervisor. Because in fact, if you're just dealing with containers, again, you just share Linux kernels, you isolate properly a process. It's going more and more to, in fact, cloud-native network functions implemented as containers running on bare metal, on a bare metal Kubernetes distribution. So you don't need the hypervisor anymore. That's very good because hypervisors have become very expensive lately. So why not get entirely rid of the hypervisor if you can do it? And this is a typical, and one of the, at least for the telco industry, the typical mobile service providers, one of the major drive to do this, to move to a containerized network function, in fact, is an evolution of the 3GPP architecture, which standardizes the different functions of a mobile network. So sorry, there are a lot of abbreviations here, they're detailed below, but the important, so all of these things make up a mobile core network. And these things which are here, UPF, AMF, SMF, etc., the latest, when you want to have the next evolution of the 5G network, which is called the standalone core. Sometimes you see this industry SA, standalone core, which gives you, in fact, more features than the first, probably what you are, I don't know in New Zealand, in fact, what you guys are currently running right now is maybe on a non-standalone core, which provides not all the advantages of 5G. And in fact, your telcos are probably still, I'm not sure, so here are still migrating to a standalone core, which give you added benefits and, let's say, the full feature set promised by 5G. And in this standalone architecture, in fact, there is a kind of prescription that all of these functions now are going to be implemented at microservices using, as you can see, a standard, HTTP APIs. So it's looking much more like a standard, IT microservices-based software compared to before. Before, the telco industry was using a lot of proprietary, let's say, not proprietary, but protocols that are not very common. With the standalone architecture, which is milestone 2 of 5G, there is a kind of prescription to move to a microservices-based architecture with API calls between these different functions. And in most telcos, in fact, this triggers, the need to host all of these functions on a container-based platform using Kubernetes as the orchestration platform. So in fact, here we are seeing, to some extent, when we are applying cloud computing to a network, we have two competing trends. On the one hand side, what you see here is that the benefit of cloud is centralization. You share resources, the basic principle of cloud computing. You have as many users as possible, so you can share the resources, and you get maximum utilization of the computing, networking, and storage infrastructure. But the telcos are a little bit different because, in fact, they have a highly decentralized computing architecture, especially if you own a mobile network. So first of all, you can have regional data centers, and of course, even what's at the bottom of a cell tower is, in fact, a small computer. So in fact, a telco is, in fact, a highly decentralized computing architecture. And even, in fact, when we are talking about IT workloads, there is a more and more recognition that, and I was just talking to someone, during lunch, they told me they're moving off Amazon, off, let's say, a public cloud-based relational database because it's too expensive. So in fact, a lot of telcos and enterprises in general are realizing that public cloud, when you use it all the time, the workload is running all the time, sometimes it's quite expensive. And also you have the data privacy, the data regulation, which might compel you as an enterprise or a telco to not put the data on the public cloud, to keep it on-prem. And on top of that, for a highly decentralized computing architecture like a telco, you may need to decentralize, by principle, these things. So in fact, the ideal is to centralize everything, but it's not possible because first of all, there is too much data, and sometimes it's better to process the data locally because of reasons of latency, sometimes better bandwidth. Sometimes also centralization goes against the principle of resiliency because if the central thing, the whole public cloud crashes, everything is down. So you want to think decentralized. So we have these two things happening at the same time. You need to do cloud computing, but maybe, especially for a telco, more in a decentralized manner. And so what we are seeing here, especially to make economies of scale, is that it's important to have, when we're talking about telcos and a highly decentralized architecture, you need in fact to have small footprints. Meaning that maybe with just 3 physical servers, or even sometimes with a single server, this little Kubernetes cluster, so it's a container-based distribution, has to host different network functions, whether it's sorry for the abbreviations, so this is something that's used in the mobile, that's maybe UPF, basically it's the mobile core router. It's the router, it's where your data goes through. And then People are also exploring, edge applications. They want to monetize this distributed computing architecture and offer some applications, to the end users. And I think that's maybe very relevant, for example, in New Zealand, because it's highly decentralized. And instead of, backhauling all the data to maybe, Wellington, Auckland, etc., you can provide, small local data centers where you can provide some services. So in this ideal, platform, you can host both the networking applications, so the CNF, such as the UPF or even the radio, which is the CU, as well as generic cloud computing application, as most of you know them, like virtual machines, containers, block file, object storage, these kind of things. But then when you want to do this at scale, so that's the problem of a decentralized architecture, you need in fact a centralized management plane, management at scale, because potentially you're going to have hundreds, or maybe even, if you're talking about a radio network, thousands of these little, individual Kubernetes clusters, but you need to centralize, the management, and you need to minimize the, let's say, the care and the number of times you need to send people on site. So this has to be highly automated, That's one of the key things to do this at scale for the edge. But at the same time, you want also what we call hybrid cloud support. Because maybe this is what you're running for production, but at the same time, you want the same platform to be used maybe for experimentation, for testing, even for scaling out when you don't have resources on-prem. So you want ideally the same platform and the same control plane, here I'm talking computing control plane, can be used on public clouds. So it's very important as well. So I understand, I think, for example, even many countries now have public clouds. And in fact, some of the software that's there can run on the public cloud and benefit from the elasticity of the public cloud, which is relevant for testing, validation, and even from some other workloads. The other thing that's very important to all of these things, it's very difficult for niche platforms to succeed there, because when you are talking about monetization of the platform, you want to have third parties to develop on top of the platform. And the third parties are only going to be attracted if your platform is very popular, which means that you need to have extensive developer tools to do DevSecOps, and to make it easier for the people who are going to make beyond the networking, let's say, workloads themselves, who are going to make business applications which are relevant for the end users. Now I'm going to dive a little bit on the radio access network. And just show you how this is being now. It started mostly in the core network of mobile telcos, and it's now being applied to some extent by more and more by people to their radio access network. So that's the one which you're using to connect your smartphone. There are two things that are happening in the radio access network. There is run centralization. We try to centralize some of the functions, and cloudification, meaning that you want to run even the radio network function, which is very appliance-based, I would say up to now, also on the generic cloud computing platform, based on containers now. And the two things that are converging here is something called the Open RAN movement, which is about making the different building blocks of a radio access network more interoperable, and Cloud RAN, which is in fact centralizing part of the RAN and putting it on a cloud computing infrastructure. And we call these two things combined together Open Cloud RAN. Okay, so very quickly a dive in the technical architecture here. The radio access network has two main, let's say, functions. One is the radio unit. So that's something that's sitting typically on top of the tower, which for the time being still remains a very specialized appliance-based hardware, although embedded Linux is running inside most of these things. And what used to be called the baseband unit, which is processing, in fact, one of the roles is to processing the radio signals and then communicating back with the core of the network over the backhaul network. These things have been pretty well standardized by 3GPP. What was not very well standardized before was the interface between the radio unit, what's on top of the mast, and the BBU, which is basically a computer. And in fact, one of the main objectives of the O-RAN Alliance was to open up this thing and so that you don't have to buy the entire thing from the same vendor. So now you can buy the BBU, which is mostly a computer, and the RU, which is still a very based appliance-based, from different vendors, and can mix and match. So it's an emerging market, I would say, and the whole purpose was, one of the goals was really to implement a multi-vendor ecosystem for the RAN. The second goal was, instead of buying appliances, for each of these parts of the network, was to put this on a generic cloud computing architecture, so typically a Kubernetes-based platform, and run this DU and CU thing as containers on top of a distribution like this. So that's more the cloudification of the radio access network. So why people want to do this? Well, the major goal was to open up the ecosystem, not to depend on 4 vendors, where you have to buy everything from them. That's, I would say, the main business goal. And it also provides, let's say, easier way to automate, because your platform, cloud computing platform, is very standardized. You don't have different silos, and can improve the quality of the service. It's a very high debate in the industry. Is it less expensive? Is it more expensive? Still be highly debated. But I think over the long term, that's the right solution. So one of the models that, let's say, we are seeing adopted by some telcos is to have one single platform, now Kubernetes-based, to host all of these workloads in their network, whether they're running on public clouds, centralized data centers, or even at the far edge when you're talking about the radio access network. And here you're just trying to reap the same benefits like cloud computing, meaning consistent operations, faster time to market, increased innovations, because we don't have vendor silos, you don't have all of these different ways to automate things. There are some, let's say, and there are press releases behind all of this. There are some leading, let's say, telcos around the world who have started to adopt this, whether it's in the IT space, in the mobile core space, at the edge, so edge computing, or even via RAN and Open RAN. So telcos are starting to do this. It's not, let's say, the generic way of doing things yet, but telcos are starting to adopt horizontal platforms for their networking workloads, not just the IT workloads. We don't have, let's say, much time, so I will, you'll have the slides. These are the important properties, of a telco cloud platform which can support, networking workloads, whether it's for the mobile core, whether it's for the radio access network, at scale, with a centralized management plane. And in fact, what is also very interesting is not just the platform, because a platform is worthless if there is no workload. It's like a gaming console, video console. It's worthless, you don't have games to play. So in fact, for these type of platforms, there are, in fact, some of the leading vendors in the networking space are already, providing their solution, whether it's the radio access network, the core, some routing solutions, some security solutions like firewalls. They have already tested, validated their software on these type of platforms, and they can deliver it. So there is, in fact, there are platforms to do that, and in fact, there are vendors who have already tested and validated most of these are, in fact, containerized, workloads on this type of platform. So it's really already possible. And last slide. This also gives the opportunity to manage the network in a very different way, in a cloud-native way. A lot. I've been, I've worked before for, Alcatel-Lucent, and I would say the way telcos, automate the network was very much manual with a lot of different silos. Once you have standardized, on a common cloud computing platform, Kubernetes-based with containers, it becomes much easier to automate the entire network. So you save on, on people. Your people can do more with less, and it's more efficient. It's more precise. You make less mistakes. So at the same time, you can use some of the very best practices developed by the IT world such as GitOps, so meaning operations using Git, where in fact your entire network, the site design, the site modeling, in fact is described in a Git repository as a text file that people can edit, update, etc. And the way you make changes to the network is not by logging onto a machine and your engineers doing this. You make changes to your Git repository. This gives you the advantage to have a complete history of changes and being able to do rollbacks. And then you have different systems like the centralized control plane that I was talking about that can automatically, let's say, deploy the different workloads of a mobile network, whether it's radio access network, mobile core, edge. And also there's another component, which is the infrastructure automation for the non-virtualized, non-containerized workloads. Typically, your routers, your router appliances, your firewall appliances. Typically, you can do this. One of the options to do this is using the Ansible, some products based on the Ansible open source projects. And we are seeing, in fact, some of the leading telcos, they're not so many yet, they have very successful implementations with this, and they're very happy with this because they're saying, oh, my people can do more with less now. It's faster, instead of deploying something in a couple of weeks, I can do it maybe in one day. And also it gives them the confidence of doing repeated deployments without any mistakes. And I think that's very much, the way that I would say networks in the future, should be, let's say, designed and deployed and operated. Yeah, that was it, I think. Thank you.
All right. Thank you very much, Michael. We can entertain one question from the audience. If you do have a question, please approach the microphone and mention your name and affiliation. Any questions? If not, thank you very much, Michael. Okay, for our next speaker, well, he actually doesn't need any introduction. We have here Jeff Houston, the Chief Scientist of APNIC, to talk about is infrastructure security a market failure? Well, let's all find out. Jeff?
Good afternoon all. Houston, I work with APNIC. Sorry I was a bit late. I was meeting with the boss, and I've never had a meeting with the boss before. Seems we have a lot to talk about. So yes, here I am anyway. This is a talk at the intersection of technology and business, because you don't work in the internet, you work in the comms business. And the comms business is actually, in terms of human scale, I think one of the most valuable activity sectors in economics. The old telephone companies were the largest national enterprise of any nation, the largest, employed the most people, generated the most value. Oddly enough, it's still generating an enormous amount of value, huge. It just happens to go into Mark Zuckerberg's and Elon Musk's pocket, but it doesn't, negate the fact that there is an extraordinary amount of value in this industry. But it's changing, and what I wanted to sort of discuss with you and look at is what's happening to the internet as we know it. And I was going to illustrate with a couple of questions, and it relates to the security of our infrastructure. I take it all of you are aware of security for the DNSSEC. If you aren't aware, you're either dead or 5 years old, because you just couldn't avoid this kind of topic, right? And the exhortations about you must sign your domain name, it's really, really good. And the woeful stories of Internet NZ that lost the internet in New Zealand for a couple of days because DNSSEC got stuffed up is certainly one of the cautionary tales of this. But the whole issue is DNSSEC is not a success story. You'd think that adding a security mechanism that prevents bad stuff from being generated would be like, selling drugs on a street corner. You'd be overwhelmed by demand, you'd think. But we're not. The opposite's the case. It's taken 30 years for DNSSEC to have got nowhere. 10% of domain names are signed. The other 90% are not. That's not a success story. It's taken 30 years for just 1/3 of the world's users to perform DNSSEC validation, and no one else does. So of all these, DNSSEC is the answer kind of folk, how long is it going to take? Will you still be alive when it ever actually happens? Because this stuff is going nowhere slowly. It's not a success, it's a screaming failure. Why? RPKI. This is not all of a sudden an answer we thought up about last week. Trying to secure the interdomain routing system is a topic that's been around, to my knowledge. There are papers that go back to about 1994 or 95, just a couple of years after the specification of BGP. It's been around forever. And it still isn't here. Everyone runs BGP. There's very little happening in security. Why is it taking so long? Again, you'd think, obviously, that a system that stops people lying in routing would be a no-brainer. You'd be fending people off. Oh, I must run it, I must run it. But in the end, we harangue you at these meetings. We constantly say, look at the wonderful things you should be doing BGP routing security. You should, you should, you should. And you're not doing it. There's no end in sight. The halcyon days where all of a sudden, BGP security is everywhere are nowhere in sight. It's not going to happen tomorrow. It's not going to happen next week, this year, this decade. It's not. Something's going wrong. Now, in a deregulated world, and surprise, surprise, the internet is not built by orchestrated, homologated telephone companies. It's a fully distributed, deregulated market of individual suppliers. As you saw in the story about New Zealand, there are folk who dig ditches, there are folk who build towers, there are folk who put microwaves on top of it, there are folk who do spectrum, there are folk. It's all pulled apart and teased apart, and each individual player is not acting on the instructions of the government, is not acting under anyone else's instructions. They're just trying to make a buck. They're just trying to satisfy their perception of market demand. And so when you see things like DNSSEC, it's really all those individual decisions aren't being made about let's do DNSSEC. And when the right thing, and if you think security is a good thing, when the right thing doesn't happen, it's reasonable to say that's a market failure. The signals in economics that say this is a good thing to do are being perverted, and you're not putting let's do routing security at the top of your list of things to do this week. It's not happening. Now, if the question is that a failure? The answer is, well, yeah, talk over, thanks, great, go to the next talk. But I think there's more to it than that. Trying to understand what's happened to the internet where security, making the internet somewhere that's hard to lie, is almost impossible to pull off, is worth thinking about. And it's not that we're all dumb or we haven't figured it out or we haven't been listening to it, the last talk about RPKI. That's not the case. There's something else here going on, and I'd like to sort of explore that a little bit about what is infrastructure security, market failure, and why is all this failing us, and what are the implications? And finally, a glimmer of hope. Can we make this better? So in terms of the internet, there's kind of this realm of routing, names, DNS names, and addresses. Names, addresses, and routing. And that's sort of the common structure that defines the internet today. And what does security do? Well, we're trying to protect the integrity. This is my address. You're not allowed to use it and claim that you're me. This is my domain name, not yours. Now, how do you protect that uniqueness of use? Because security is actually about enforcing that, and then if anyone else attempts to do that, the lie, the mistruth that is implicit in using someone else's address or someone else's domain name should be evident to anyone. That's the wrong place. That's not your bank. That's not the person who is in the from line of that email. This is a lie. And folk use the internet day by day on the assumption that what they're seeing is the truth. Hi, what's your client number? What's your password? Well, I'm only going to tell you if you're my bank. How do I know that you're my bank? Well, I don't know. It just looks the same screen as before. Let's just do this. You trust the internet to a level that's breathtaking, yet underneath it all, a lot of the security instruments that are meant to actually carry that trust do not exist. So you'd think making it better would be a no-brainer. You'd think that security, protecting that, should be easy peasy. Now, it's failed. So let's talk a tiny little bit about market failure. Investopedia is your friend. It's a situation where the individual incentives to do things don't match the common good. DNSSEC is probably a really, really good thing. But security can't tell you what's bad. Bad people don't sign their messages saying, "Hi, I'm bad, don't believe me." The best security can do is sign what's good. Now, if everybody who's good signs what's good, anything that's not signed is bad. Because if it was good, it'd be signed, you'd be fine. And so security only works by the, if you will, negation of positive. Security doesn't tell you what's bad. The absence of secure credentials allows you to infer it's bad. But what if all of you people, sign your stuff? And you folk, naughty, naughty, don't. And I see something that's unsigned. Well, it's either bad, that's the people in the middle, you're bad, or it came from you because you're just not signing. I can't tell the difference. And so in this kind of security world, the problem is that everyone needs to adopt all of the time. And a market failure occurs where the incentives to sign for everyone don't exist. We all have different incentives. Now, the other part of this is market failure is a public good. What's a public good? The air we breathe, the water we drink, that kind of stuff. Stuff that's non-excludable and non-rivalrous. Because you do it, I can do it too. You don't exclude me. We're not bidding for a finite resource. A good is a simultaneous common resource that all of us use. So this is where we're working from. And as I said, in deregulation, in a post-telco world, everything is done because of market pressures. Governments don't tell folk how to invest their money in the internet. They don't. There's no forcing function. You do DNSSEC because you chose to. You do RPKI and routing security because you chose to. No one's forcing you. There's no one there to tell you that you must do that. And so what the internet has relied upon and what we've constructed over the last 30 years is just this perception of opportunity and cost, that we all think you're subject to much the same pressures. And if I think, signing stuff with rowers is a good idea, you probably think that too, and we're good. And it kind of sort of works on the assumption that the industry works on common self-interest. Yeah, right. Yeah, right. And what we're living through is the nightmare that says that isn't the case. Because every market's different. Every player is different. Why hasn't everyone done V6? It's a no-brainer. We ran out of V4 addresses. NATs are complicated. They make your life hell. Applications don't like them. So why do you still run them? What are 60% of the world's users still running in V4 and have no V6 at all? Why do you do this to yourselves? Because we're different. We don't see these problems with a common perception of what we should do and when. Everyone reacts differently. And so when you do something like security, that only works when all of you do it. Because that's the only way you find bad. When everyone signs good, the absence of sign is bad. That's the only way security will work. Well, it's a failure because you're not all finding that pressure. Only a small percentage of you are doing it. Why not? Have you just not heard? I doubt it. Do you think you don't need to spend the money this week? More than likely. And there are really good reasons why a lot of you go, I don't need to spend the money, my margins are slim enough already, I'll defer. Because my business will still be around tomorrow, this is not an essential expenditure. I can defer it. I don't need to do V6 this week, or next week, or this year, or maybe even this decade. No forcing function, I'm okay, I'll just keep on going. And that's where this industry has come to. The common perception of cost and benefit are different for everyone, and some folk are perfectly fine in actually not doing it. How much V6 is there in Nigeria? Almost 1 billion people, almost no V6. How much V6 is there in India? About 1 billion people, everyone has V6. Economically, Nigeria and India, similar developing kinds of economies, similar kinds of technology environment, different decisions from both national areas, different. It's not that one's right and one's wrong, different pressures in heterogeneous situations give different outcomes. So that's what we're seeing here. So as I said, adoption is variable and not everyone has the same perception of benefit. So when you say, and we do, when we harangue you about how wonderful it is you should all do routing security, you know, it's in our common interest to do this, most of you aren't listening. You're not listening to the extent that you go, oh yeah, fine, I'll do it when I get round to it. There's no great hurry. I don't need to do it today. So adoption becomes irregular, variable. It just doesn't happen. Why not? I deploy RPKI. I do the right job. I do route origination validation, blah, blah, blah. I've gone through the whole song and dance. I tell my sales force, this is great, go sell it to customers. And the issue is, I've done this, why? Because it was a Wednesday and I had nothing to do? Well, and theoretically, as a business, I only did this expense because I expected more income. I expected that I could charge a premium or gather more customers from my competitors if I was doing this. Does anyone charge their customers more because they have routing security? No one. It's not a sales thing. Customers don't even understand what you're doing. It doesn't translate into a product or service that is a premium. And Mike, let's go to the DNS. Does anyone charge more for DNSSEC? The only way Sweden did almost complete adoption of DNSSEC signing is by charging registrars 10 to 15% less. They created the false economic incentive that DNSSEC was cheaper, whereas in reality, it is more expensive, there is more work to do, and there's more stuff that goes wrong. Hello.nz, right? So somehow charging less for doing more is not a way for business success, it's a way for complete business failure. So somehow we can't monetize the right thing. And if we can't monetize it, it doesn't happen. And I can tell you till, blue in the face, it's really good. Routing security is important, DNSSEC is important and all that. But you're not listening because the money is saying something else. The money is saying, can't charge more, why should I bother with the cost of doing it? How many routes are without rowers? In V4, what does that graph say? Half the routes still don't have rowers. Half. Oh, it's going down, it's getting better. For how long? How long will this take? How many decades? Same in V6. Same story. So around 54% of all advertised routes in the V4 space are not listed as a rower. They're not. 48% in V6. And no one's doing path protection. Nobody. Probably because we can't, but even so, it's not there. And don't forget, without path protection, the whole rower thing is kind of a fiction, because I just fake the origin and you can't tell the lie from the truth anyway. So in some ways, there is no hope here. This really looks bad, and it's no idea of how long it will take. DNSSEC validation. 70% of users will accept an answer from the DNS even though it's crap. Just under 3/4, even though it's crap. They'll accept it. That's good. 90% of the Tranco top 1 million names, 9/10 aren't DNSSEC signed. No one cares. It's not there. And I would actually argue it's never going to be there. And in terms of securing addressing, you look up a registry database from APNIC or Aaron or anyone else, how do you know it's true? Well, I've gone to the right URL. So, how do you know the content is true? How do you know the description of me as a resource holder is true? The answer is, well, I went to the right place and I found this, so therefore it must be true. That's not good enough. You know, why aren't these things signed? Why haven't I signed them? It's about me, it's my data. Surely I should be able to sign it with my key to say, trust this because I wrote it and I can't refute it. And you know, if this works for rowers in theory, well, why doesn't it work for anything else? We haven't got the addressing infrastructure secured. It's kind of ripe for a problem here, and that's not good. So now let's move up in the infrastructure model. Some bank has contracted me to write their banking app. Great. Can I count on the presence of RPKI so that I don't have to do as much work? Well, of course not, because a massive amount of the internet doesn't have it. Can I count that the DNS never lies? Well, of course not. As an application, I have to assume a hostile environment where the infrastructure is unprotected. So whether you do it or not makes no difference to me, the application designer, and the customer. No difference at all. They have to assume that everyone is not doing it because that's the case for a large amount of the case. So all of a sudden you have to do your own security solutions. So if you can't get infrastructure security, you have to do your own form of doing that. You have to do your own form of security. So what do? Any answers? Oh, come on. Does anyone still run a web page of http:// other than the Bureau of Meteorology in Australia? Nobody. Because whenever you do, you get this warning from Chrome going, this is bullshit, don't go here. And they're right. Applications went and did something different. They solved it at an application level with TLS. No matter what the infrastructure does and directs your packets, your opening connection, if where you are can't demonstrate that they are authentically the name of the service you intended to go to, TLS won't complete. It'll give you a warning. Now, if you're fool enough to go, well, okay, I reckon it's true, I'll contradict you, more fool you. The Ether wallet problem, right? As long as you go, if the certificate, the TLS isn't working, it's a bad site, then that's what applications do. How much TLS is there out there? Not 30%, not 60%. Cloudflare Radar says 97.2%. That's adoption. How many talks did you go to about why TLS is a wonderful thing? None. TLS sold itself. The browser vendors basically said, look, it's time, we all should do this, and if you're not doing it, we're going to give huge warnings to folk going, this is a crap site, don't go here. So you all did it. And by and large, this is what the Internet Security Framework relies upon. It doesn't rely on DNSSEC, it doesn't rely on RPKI, it's totally reliant on TLS. So if TLS is actually there, why do I care about DNSSEC? I don't know either. Why do I care about secure routing? Because if my packets are going to the wrong place, you haven't got the ability to open up an authentic TLS session. It won't open. So why do I care whether you're doing it or not? I don't know either. And this is part of the reason why, when we try and sell these things going, they're really, really good, the true resistance is, but we've got TLS. What's your problem, dude? You know, why do you worry about this stuff? It's not that important to us. We have a solution that we're willing to live with. So once you've got TLS, why do you need RPKI or DNSSEC? Well, you don't. You place a zero value on it. So you can do all you like in DNSSEC or RPKI, whatever. The applications world is saying, great, hope you had a good time. I don't value it. I'm not going to pay you any extra money because you've done it, because that's not part of the deal. The value that I place upon this is zero. And that's why most of you don't do it. You sit there and go, why should I waste my time doing stuff that my customers and clients and applications don't value? Because they have an adequate solution. It's just not your solution, but for them, it's perfectly adequate. There's something deeper going on. And it does reflect upon Mark Zuckerberg, Elon Musk, and the rest of them. Deregulation actually meant a massive shift of trillions of dollars across the last 30 years. Because previously the telephone companies were the orchestrators of the service. They ran the network, they ran the switches, they ran the wires, they supplied you with the handset, they billed you, and you talked, and you paid for talking. And they internally redistributed amongst their suppliers. You couldn't supply unless the telephone company had blessed you as a supplier against their technology. They saw themselves as network operators and collected all the money and redistributed it to others. That was the old model, and it was the model where the internet was built. And for a small period of time, around 95 to about 2005 or so, the internet service provider business was actually quite a lucrative business, and there was a lot of focus of attention. And many of you probably cut your teeth being in an ISP world. Few of you are there now. The money's gone. The money's gone. Where's the money gone to? Well, it's gone into applications, because applications found a way to use the internet to reach directly and charge you. I didn't need a network in the middle to broker that relationship. So how many paid subscriptions do I have for video services? Probably as many as you do, a lot. You know, how many deals do I do at the application level all the time? Because what the network facilitated was the applications disintermediating themselves from networking. The network becomes commoditised and valueless. The industry down at infrastructure is now starving for oxygen. There's nothing left. All the money has moved up to the Googles of this world, and they're effectively greedy. They don't share, they take it all. And that's what's happened in this industry. The last 2 decades has been a shift of value to the top of the protocol stack. And what about applications, or at least protocol engineers like things like QUIC? It takes the value of the operating system and that common set of code and lifts it into the application. QUIC is just UDP. All the work is done at the user level inside the app. We're busy making the entire internet an application space and making sure that operating systems and transports and networks are kind of valueless, just infrastructure. They're not separately valuable in their own right. So the current model is the value transform has gone up the stack. And quite frankly, this service model is now application-centric, not infrastructure-centric. Where's the local data centre for Wellington? Well, in Wellington. When you stream Netflix, where does it stream from? Well, Wellington. How much traffic actually comes across the planet to come to you or me when I'm here in Wellington? Very little. Very little at all. So in some ways, the lower layers of the stack have been eliminated by these content data networks. All of a sudden, we're not one cosy little family. The application folk hate the networking folk with a vengeance. Encryption is their friend. QUIC is not encrypted just because you can. It was encrypted to hide what you're doing from the network operator. Mutual distrust and suspicion. And the application basically defends itself by wrapping it up in deep layers of encryption. Look at QUIC, look at MASK. So at the network level, you can't see what's going on. You have no control. You can't differentially charge, nothing. For the infrastructure operator, security doesn't matter. No one values it. Nothing. So who's going to invest? Who's going to fund it? What a great question. I have no idea. DNSSEC needs more money. Well, fine, it probably does. Who's going to pay? I don't know. Do you? I doubt it. You know, this is just, we could do a better job, but no one values it, so why bother? What about BGPsec? Same answer. Exactly the same answer. It's the economics that's killing us, not the technology here, if you think this is a good thing. Because TLS is good enough. Whatever good enough is, it's good enough. So maybe I've been a bit extreme. Should we try and fix what we have? Can we improve TLS? Well, of course we can. Is anyone going to pay to do it? Whoa, interesting. Somehow I kind of doubt it. Apple's leading the charge with its use of MASK and Apple Private Data Relay, But quite frankly, the uptake is minuscule in the larger scheme of things. Oddly enough, all of that technology, users don't value it. They just don't. It hasn't made a dent in their iCloud subscription levels. It's just not something that users are really that interested. Why? Moore's Law. Computing has been doubling consistently every sort of 2 years or so for the last 30-odd years. Communications has not. It's cheaper to put more computing and processing everywhere around the planet and replicate content than it is to actually build a network to shift the content around on demand. And that's the network we have today. There is no network, it's just a last mile switch. Everything else in the middle is done privately inside private corporate CDN networks. Nothing to do with us in the public net. So faster, cheaper processing has actually led to a completely different network. Nobody routes. And if nobody routes, nobody cares about routing security because nobody routes. That's the problem. So the common network is now devalued and almost unused. We just switch on last mile. And the failure to achieve, things like routing security, DNSSEC, etc., is actually a broader commentary on the fact the network is no longer what you thought it was. There is very little common infrastructure other than that last mile access network. The true battleground is actually down there in getting to your house from the local data centre. And so what do governments do when they see this market failure? What do governments do? Oh, we must make security a mandatory. We must do like the FCC and make BGP security a mandatory feature of the environment. It might have had an impact 20 years ago. Today, it just seems like an anachronistic piece of blathering from folk who just don't get it. Because the market's moved on. This stuff doesn't matter anymore. And no matter what the FCC does and the latest pronouncements, and there was one yesterday from the latest sort of election furore about how routing security will remain mandatory under our new FCC, just missed the boat by decades. Because, quite frankly, it's a different internet. Quite frankly, it's not the thing you knew. This is a last mile switching infrastructure and it's a completely different set of demands. Do you need DNSSEC everywhere? Well, I don't know. I've never seen a compelling case and neither have you, because if you had, you would have done it. Do you need routing security? Again, if you needed it, you would have done it. You're not dumb, but you haven't. So therefore, there were reasons why. So what do we need to do? How can we improve the situation without trying to make anti-gravity work? I'm not sure. And this is not a talk about answers, because I have none. But it is a talk about saying, look carefully about the messages you're getting. And when the exhortations are, you should do V6, you should do this, you should do that, think about why, and think about why folk think you need to be harangued into doing something you weren't already doing naturally. Because if you weren't doing it naturally, if it didn't make sense yesterday, hardly likely to make sense today. And so what we've got, TLS, whatever, is, I suspect, what we're stuck with. This is the world, make the best of it. Thank you.
Thank you, Jeff. I think we only have time to entertain one question, but the question is coming from the remote participant, so I'll read it out. Thanks for your presentation. The question is, DNSSEC has developed slowly. I think DNSSEC is very complex, and once it breaks, the consequences and impact are significant. He cited the most recently, that RU affecting the internet for 8 hours. So the question is, do you have any plans to replace DNSSEC?
TLS. TLS says, are you in control of the name of the service I'm going to? I don't care how the DNS gave me your IP address. I don't care. But if I've gone to the right place, you can tell me you're real. And you go, well, the DNS can send you to the wrong place, but the wrong place can't tell me that it's genuine. Oh, that then leaves you with the denial of service attacks. And I'm going, there is a dictionary of denial of service attacks that have hundreds of millions of ways of stopping you from getting to the service you need to get to. Plugging one hole leaves the other 999 million still there as holes. That's a different problem. And thinking that all of this security is going to solve all of those problems is kind of fanciful. DNSSEC doesn't actually solve the issue. And interestingly, it's a long answer to a short question, when you look at the first spec for DNSSEC, the RFC, it said this is only part of the problem. It's still a larger problem about how do I get to the service I want to get to. We're not going to answer that with DNSSEC. And they were faithful. They didn't answer it. TLS decided the other way. Am I reached the genuine spot? Yes, fine, I'm there. I don't care how I got it, I'm there. And it was that failure, I think, on the technology side with DNSSEC that back in 1994 doomed it. It was never going to work. Oops. Have I offended all of ICANN yet? Okay, thank you very much.
Thank you very much, Jeff. That was a very good talk. All right, we're down to our last speaker. We have Ulrich Spiedel. He is obviously a well-known participant of the NZ and Pacific Internet community, and his work as a senior lecturer at the University of Auckland. His body of work includes all levels of the telecommunications protocol stack. All right, here to talk about Starlink and how fast Starlink can really be. Ulrich, you have the stage.
Okay, sorry, I think the microphone went walkies, and I tend to walk around, so I'm not like Jeff and able to concentrate on two microphones in front of me. Okay, so yeah, welcome everybody. So I guess you've all heard about Starlink. Anyone here who hasn't heard about Starlink before? Nobody, great. So I don't really have to introduce it very much. So basically, just for those of you who are maybe a little bit shy, putting their hands up saying you haven't heard about it, what is Starlink? Well, basically, if you go to their website, that's what it says. And I'm a cave dweller. You know, I have one of those man caves at home, and I always wanted 100 gigabits per second in my cave. Can I get this from Starlink? Well, it doesn't really kind of tell me much about this. Well, it does tell me that it's a satellite service and that it's you know, basically forcing me to put the antenna outside my cave. Now, that's not a great thing if you're a cave dweller, but okay. And somehow it's using a satellite, and whatever satellites are, there's those things up there somewhere. And well, currently they operate over 6,000 satellites in low Earth orbit, number growing at mushroom speed, and basically have around 3 million users worldwide, or customers anyway. And they're sort of meant to be mostly rural and otherwise underserved. And when we look at the downlink rates on the user downlink that we see, we can sort of typically get something between a couple of dozen megabits per second and about 400 megabits per second. So, strange thing, it varies. Why the variation? So what do we actually know about Starlink, and where can we find out about Starlink? Now, it turns out the SpaceX folks, or these are the people who are behind you know, the Starlink, they don't really reveal much. If you go to their website, most of what's on the website in terms of specifications, you can figure out for yourself with a tape measure and a power meter. So this is about as much as you get off them there. Then, of course, there's this you know, enormous resource of truth in the gospel, known otherwise as Reddit. Anyone relies on Reddit for anything legal? No? Okay. Right. And then, of course, you know, there's you know, Starlink's X account. I just do wonder why they do go to X. Apparently they've got the same owner or something like this. But yeah, for all practical purposes, there is one spot where you do actually get relatively reliable information from, and this is a crowd that's already been mentioned by Jeff earlier on. It's the FCC. And although Jeff didn't really have a lot of good things to say about the FCC, this one thing about the FCC is if you do put an application to the FCC, and SpaceX have to do this in order to run their Starlink stuff, basically what they have to do is they have to fess up, and if the FCC gives them a license to launch and operate, and they get licenses from there in order to operate their ground stations, also, by and large known as dishies, if they're not on the infrastructure side. So end user side are those things called dishies. There are different shapes of them, but they're basically by and large the same. So they have to operate within the terms of their license. And so if you know what they've applied for and got licensed for, it gives you a bit of an idea about the parameters within which they can operate. So the thing, of course, is these are documents that are by and large written by engineers in conjunction with lawyers. And the lawyers are basically there to make sure that anything that the engineers write is obfuscated enough so it takes the other side, the people who like to throw spanners into the works, and these are the people whose lunch Starlink is currently eating. These lawyers are basically paid to make it as hard as possible for any opposing party to A, find anything in there that they can rely on, and B, anything that Starlink isn't going to change 5 months later, or 2 months later, or 2 weeks later. So basically the name of the game is, if you are SpaceX, you want to make sure that your competitors spend as much money on lawyers as possible and as little money as possible on doing technological development, while you want to spend as little money on your lawyers and as much money as possible on getting your technology developed. And similarly, if you're not SpaceX and you're a competitor, your lawyer's job is to throw as many spanners as possible into Starlink's works. And so a lot of the information that you find in the FCC filings seems to be there specifically to throw the competition off your track or get them playing with some red herrings that you're then going to abandon sooner or later. So in other words, there's an enormous amount of FCC filing material, and working through this takes a little bit of time. And when you're an academic like me, you can only really do this when you're on sabbatical. And luckily this year I've been on sabbatical, and so I spent a few weeks at IIJ Lab in Tokyo in Japan, hosted by Chris. Chris, you're here? Wave your hand. Acknowledgement. Okay, now he's probably over in the other session. So for all practical purposes, managed to read through most of this, and so I came to a bit of a conclusion. And that's what really this talk is about. Now, this talk normally, takes about an hour to deliver. I've got about 18 minutes left, so I've got to compress a few things. However, if you want to download my slides, they're about 290 megabytes because there's a few movies which we're going to, partially watch in a moment. So there's speaker notes on this, and they contain a lot of detail. So do look at that if you want to know a bit more. Okay, so for all practical purposes, what are the ingredients that we need if we want to know how much Starlink is really capable of? So for one, we need the constellation information. That we can actually find from the FCC filings and the FCC licenses. We need frequency and band information. Again, that comes from the FCC filings. Beam information. Also, it's interesting, when they're having their beam information, every time they're amending an application, they're having to list their beams again. And they're doing this in a completely different order every time, just so the lawyers of the opposing side and poor people like me have to check that nothing's changed. So regulatory compliance information, we can get that from the FCC filings and related ITU documents. We can get the signal level information, and this is interesting because if you're trying to get signal level information from a system that transmits it to you from different distances and different angles, you think this might be difficult, but it actually turns out it's not all that difficult because in the FCC filings you find a gem of a passage which basically says that Starlink satellites adapt their transmit power on their beams in such a way that the power that is incident on the antenna is pretty much the same no matter which direction the antenna is receiving from. And that makes life a hell of a lot easier when you're then trying to do your calculations further down the track. Then you want to know the gain that the Dishy antenna is capable of. That is both available in the FCC filings and, interestingly enough, also on the Starlink website. And if you know what frequency it's operating on, which again you get from the FCC filings, you can also compute this yourself simply from the physical dimensions of that thing. They need modulation information, which is available from published research and FCC filings. Cell information, so it turns out they're using the same concept of a cell as Uber does, and that again makes life a little bit easier. And then you need to know about a technique called link budgeting. Just sort of as a quick question, who's done a link budget before here? Handful of people. Now, you're RF engineers by training? No? Who made you do a link budget? Were you my students? Okay, no, maybe not. Fine. So anyway, that's standard practice in communications engineering. And then you need a thing called the Shannon-Hartley capacity theorem. Anyone here remembers the Shannon-Hartley capacity theorem? Oh, gets thin on the guy. Hey, we're going to be talking about this, right? So, but we need to start a little bit with a quick course in orbital mechanics. So basically, this little white dot that you're seeing up there is a satellite. And I'm going to make that move. By the way, what you're seeing here is a video from a simulator that Toby, who sits in the last row back there, if I'm identifying right, Toby, put your hands up. So he's basically written the code for that simulator here, and I've simply plugged a bit of satellite data in order to produce those movies, and then I've taken those screenshots. So what we're seeing here is we're seeing a satellite orbiting, and so it literally goes around, and it's orbiting at a so-called 43-degree inclination orbit, which basically means it bottoms out at 43 degrees south. And when you look at how it's going, back up further north, you'll notice that it sort of tops off at 43 degrees north as well. And also, as it's orbiting, you can't see this here because we're literally sort of moving this around, but the Earth is actually spinning underneath as well. So this satellite really doesn't return to the same place for a long time, typically a few days after it's flown over a place. So the first time we flew over here, we actually flew over California. Now we're flying past it. And all of this is running at 100 times the normal speed that you would be getting. But what you can take from this is if you're at a particular ground station, you see this thing's not far away over the Earth's surface. That's the end of the movie. And so basically, you can only see this literally for a few minutes at most, and that's basically it, and then it's gone. So any communication that you do, if you want to do it over a 24/7 period, requires using more than one satellite. So I'm going to quickly go past this one without really running the video. So this is just meant to demonstrate that the height at which a satellite orbits determines how frequently it circles the Earth, how quickly it circles the Earth. So the general rule is the lower down you are with your satellite, the quicker it orbits. This is why the good old geostationary satellites that people mostly used before Starlink, they're up 35,000 kilometers something in the sky, and they move so slowly that they're literally synchronized with the spinning of the Earth, and that's why you can take a satellite dish and just point it at it, and the satellite moves with you as you rotate around the Earth's axis, and so it always appears to be in the same position. You can't do this with the Starlink satellites. They basically just rise and set like the sun or the moon would do, just faster. Right? So, as we go from this, as we go from this, of course, if the satellite's not going to stay above us for any length of time, we need more than one satellite. And so the first building block that we're having there is a so-called orbital plane, where we're having multiple satellites following each other on the same orbit. So this is what we're seeing here. And as we're moving this around a little bit, we can actually see that this literally does form a geometric plane that goes through the center of the Earth. And if we do take those, one of those planes and we replicate it multiple times and then just sort of tilt it a little bit around the Earth's axis, then what we're getting is a so-called shell. So what we're having here is a multitude of those orbital planes. And what you can already see here is an effect that's quite important for Starlink. And this is that when you're going to those latitudes that are close to where the satellite is the satellites are topping off in terms of their inclination, so in this case close to the 43rd parallel, then what you're seeing is that the satellite density there is much, much higher than it is over the equator. And that has a sort of few practical implications. So if I then run this, so this is essentially what you're seeing here. However, that's idealized. So in practice, if I look at the 43-degree Starlink constellation, what I'm actually seeing is this. And you may have sort of seen those Starlink trains going through the night sky. These are essentially recent launches of satellites that are just on their way to their final station, and they haven't spread out yet in their particular orbital plane. But again, here you're seeing that as you're near the latitudes where things top or bottom out, you get higher satellite densities than around the equator. So I can then take multiple of those shells to put together an overall constellation, and so this is what Starlink's constellation looked like in May, running at 100 times the normal speed. And as you can see, we're covering pretty much the entire globe, with the Arctic and Antarctic areas getting slightly lower satellite densities, and also the satellites that are flying there are a slightly older version than most of the ones that are flying elsewhere, and they don't quite have the same level of performance than the others. Okay, so, but just because you can see a Starlink satellite from your dish, it doesn't mean that that Starlink satellite's allowed to transmit to you. So, for example, you may have heard that Starlink satellites have to be at least 25 degrees above the horizon to talk to your dishy. That's got nothing to do with your dishy as such. This has to do with the fact that if we have a terrestrial microwave link that's operating in the same frequency band, and the receiver of that is close to your dishy, and it's sort of looking out to the other end of the terrestrial microwave link, and you'd basically at that point see a Starlink satellite just above the horizon, and that one was to be transmitting, then it could be interfering with the receiving dish of the terrestrial microwave link. And we can't have that, and so therefore you must have your Starlink satellite transmitting from at least 25 degrees above the horizon. In that case, that dish is safe from direct interference. So there's also another problem that you need to solve. What happens if you happen to look at the sky and the Starlink satellite that you want to get data from happens to have a geostationary satellite lurking behind it? Well, then there is an ITU regulation that basically says that in this case your non-geostationary, in other words Starlink satellite, isn't allowed to transmit. And so when you're looking at the obstruction map, for example, around the equator, so this is a shot that my PhD student Wayne, who also sits back there. Wayne, put your hands up. Yeah, very, very big one. Big wave, Wayne. Okay, so this is one that he produced when he deployed in Kiribati. So this shows that we're having this strip literally from west to east, where we're not communicating with any satellites, and this is because this is literally the geostationary orbit above the equator that you can see there, and we're just not allowed to talk to Starlink satellites that are in that area. Or rather, they're not allowed to talk to us because there might be geostationary satellite receivers close to us that might be listening to the geostationary satellites, and they take precedence. Okay, so if we then look at our particular latitude that we're at, and we're looking at how many Starlink satellites we can see on average over the horizon. That gets us up to over 50, and if we happen to be sort of around the 49, 53, it's 49, 50 degrees. If we're around Wellington, what latitude is Wellington? About 44 degrees, not too bad, right? We're still getting about 50 satellites that we can see, but out of those 50 satellites, we can basically use maybe about 36. The others are excluded because either they've got the geostationary arc behind them or because they're too low on the horizon. So, the other thing that we notice, if we're close to the equator, so at low latitudes, then we don't really get a lot of satellites to talk to, or that we can choose to talk to, or that we can choose to have talking to us. And when we're going to the Arctic zones, so anyone here working at Scott Base or having friends at Scott Base, again, same problem, or one of the other Arctic bases, same problem, not a lot of coverage down there in terms of number of satellites to pick from. Okay, so now let's have a look and see, if we can see a satellite, how much can we actually pull from that satellite? And as it turns out, it doesn't really matter whether I'm looking at how much an individual satellite can transmit to me, or whether I look at multiple satellites, because whatever part of the downlink spectrum an individual satellite does not use could be used by another satellite to downlink to me. But I can't take two signals from two different satellites at the same time. So it's basically like saying if I'm wanting to receive red light, and one of you sort of sending a blinking red light at me, then if two of you send blinking red lights at me, you're going to be interfering, right? So what do we need? Well, we need all those wonderful pieces of data, and then we need the effective size of our dishy antenna, the temperature of the antenna or receiver that we're operating at, and the ratio between the received signal power and the noise power that we can compute from that. And now remember that blue line there, because that's an interesting one, because as it turns out, SpaceX takes care of already computing everything up to that blue line for us. So there isn't really a hell of a lot of extra required that you need to figure out from there to get to your signal to noise ratio, and that then lets us compute things. And how do we compute things? Using this famous Shannon-Hartley capacity theorem. So the signal to noise ratio is this animal over here. So if we've just computed this, and we know the bandwidth, and we know that from the filings, then what we can basically do is we can apply the logarithm to base 2 and everything, and we get this funny C out here, and the C just so happens to be the beam capacity of the beam whose bandwidth we've plugged in here, and obviously signal to noise ratio here. So this gives us an idea of the maximum number of bits per second that that beam is physically capable of throwing at us. And then all we need to do is sum up over the number of beams. Now, this is what happens when you use artificial intelligence and you ask it to give you a picture of a satellite sending beams down to Earth. The beams are clearly fairly unstable here. They're bending in space. I'm not exactly sure what is happening here, but this is artificial intelligence for you. Makes no sense. Now, if I look at the beams, how can I characterize beams? Well, firstly, by the bandwidth that they're using, the operating frequency or carrier that they're on, the polarization, left-hand circular or right-hand circular that they use, and the purpose, whether they're a gateway beam, a user beam, a telemetry and control beam, etc., up and down, and the beam width. So as it turns out, some beams from the same spacecraft are identical, are clearly not meant to go to the same cell. So all we need to do is get a unique set of or the maximum unique set of beams that we can have, and that then gives us our capacity. And this is what we get when we do this. So if we take the generation 1 satellites, the old ones, into a single cell, if I direct all of my beams that I've got available that are not duplicates into a single cell, then I can basically get 12 gigabits per second down. With the generation 2, if it's fully configured, I should be able to get 20 gigabits per second down, and this is on Ku band. And that's important because the current dishy is only capable to do Ku band. If I go over all beams from the satellite, I get a wee little bit more. so 16 gigabits per second, but I can't direct that at a single cell, so I have to spread that over multiple cells that are geographically diverse. So when I then go to the version 2, I get 20 gigs or 48 gigabits per second respectively. And if I then also take Ka band into account, which we can use with the recently announced community gateways, but not with your normal Dishy, but assuming for the moment we had a Dishy-sized antenna, then this is what we would get. Now, with those community gateways, we should theoretically be able to go a bit larger because they can use larger antennas as well. But this is just a calculation on the basis that if we ever got a Dishy, something with Dishy dimensions that was able to do Ka band, then that's what we'd be able to expect. So take those numbers with a bit of a grain of salt here. Okay, so what does this mean in practice? In practice, it means that sometimes we may be running out of capacity to an individual cell. So this is a resolution 5 cell, for example, next to Auckland that was recently running out of capacity, couldn't be served for a while. And if we look at the average cell deployable capacity that we're seeing from the ground, then that basically means, again, we might be seeing, up to, on average, sort of minimum, up to maybe about, 200 gigabits per second at the equator. Now, this doesn't mean that a single cell can get this. A single cell can only get the numbers from the previous slide, but what it means is that I've got sort of multiple islands, for example, in an island group that are relatively close by, then this is roughly what I could be deploying across that island group. So for example, across all of Tonga, we'd be looking at around 20 degrees south, we'd be looking at around 200 gigabits per second that they can pull down, push down to Dishys, in total. So this is what we'd get if we've got a sort of, larger, country where we need to cover a larger area. So in this case, we can go a wee bit further because now we've got multiple beams to deal with. Okay, so the question is how can that possibly be scaled? Now, using additional Ku and Ka frequencies, again, thinking about going to direct-to-site Dishy here, with some serious band plan changes, maybe a factor of 1 to 2. So not really a lot. More satellites, it doesn't change the per cell capacity that we can do, but what it allows is to commit more of the total beam capacity equivalent of a satellite to individual cells. So there's maybe a factor of 30 in there. If we use narrower beams, so would use cells that are a bit smaller, we could probably, again, sort of multiply this with a factor of 2 to 5. And by the use of community gateways where we can use larger antennas, we might get to a factor of maybe 4 to 5 over Dishy with what I've seen published so far. Okay, so conclusion from there. FCC filings aren't always boring. You can country numbers, but you've got to find them first. And basically, it shows that Starlink is quite limited. So for Dishy, certainly Ka band is missing in action, but for the community gateways, it sort of seems to have just reared its not so ugly head. But also here, the potential for growth that we're getting there is quite limited. And that's something that we're seeing in Starlink's continued attempts to try and manage user density. And if we're looking at the growth that we're seeing, in historic, internet, developments, sometimes, 30, 40%, growth in volume per year, then I would say we've got to be a bit careful as to whether Starlink will be able to deliver that. Probably not that easily. Okay, and that's pretty much it from me. Thank you very much.
Thank you, Ulrich. We can probably take one very quick question, if anyone has any. Please specify your name and affiliation, please.
Hi, my name is Tejas. I'm from Bangladesh, where I run an e-commerce company. First, thank you so much for that. That totally blew my mind. I have a quick question. So what happens when more competitors put more constellations in space? How is the interference gonna, are they gonna keep trampling on each other, and how are they going to coordinate that?
That's a really good question. Now, for one, in terms of competitors, I personally only see one serious competitor coming up, and that's going to be Amazon's Kuiper constellation, if and when they acquire the launch capacity that's going to enable them to put that amount of capacity into space. The thing is, they'll have to spectrum share with Starlink. So whatever they're going to be using is going to go at Starlink's expense. And so really, they're just going to eat into Starlink's capacity at the end of the day. It's not going to make a great deal of difference in terms of extra capacity. It might obviously, change the cost involved, because then have two competitors as not a monopoly provider like at the moment.
All right. One last question, anyone?
It was really bright here.
Okay. All right, that's it. Thank you very much, Ulrich.
Thank you.
And I think that concludes technical session 1. We would like to thank our speakers again, Michael, Jeff, and Ulrich. Thank you, everybody, for joining us. And if you would like to join technical session 2, it will be happening after the break in the other room. For anyone online, there is a session poll. Please also fill it. Thank you.